Yeah, good evening, students. So, in the previous class, we had a discussion on pipelining of the instruction execution and how we can estimate the performance of the processor that we have seen. Now, today we would like to discuss about the branches and data dependencies and how we can identify the out of order execution. So, now I would like to share my screen. So today's classroom discussion topic is on branches and out of order execution along with data dependencies. The lecture objectives are, so this session will develop students' knowledge in understanding the issues related to the branches and data dependencies and what are the out of order execution. These are the two important objectives for this today's session. So branches, if you consider no branch instruction and there are no data dependencies between the instructions, we already saw that the throughput is always maximum by executing the instructions in an interleaved manner. So if a program contains the branch instructions that change the execution flow and the data dependencies between the instructions are there, so which imposes the sequential ordering constraint. So we have seen that a superscalar processor must ensure that the instructions are executed in the proper sequence. So memory delays due to cache misses may occasionally stall the fetching and dispatching of instructions. So actual throughput is typically below the maximum that is possible. So this we are already discussed in superscalar operations. So we have a fetch unit. So it will fetch the two instructions in one clock cycle and store those two instructions in the instruction queue. And the dispatch unit will read the two instructions for decoding of that particular instructions from the instruction queue. Here, the fetch unit is used for handling of these branch instructions as it determines which instruction to place in the queue for dispatching. So it determines the fetch unit will determine both the branch decision and the target address for each branch instruction. So the branch decision may depend on the result of an earlier instruction that is either still queued or newly dispatched. So stalling the fetch unit until the result is available can significantly reduce the throughput and is therefore it is not a desirable approach. So instead of that, it is better to employ a branch prediction technique here. So the aim is to achieve high throughput. So the prediction is all combined with a technique called it as a speculative execution technique we are using here. So that speculative execution how we can use here. So in this particular technique, speculative technique, subsequent instructions which are based on an unconfirmed prediction are fetched, dispatched, and possibly executed, but are labeled as being speculative so that they and their results may be discarded if the prediction is incorrect. So the additional hardware is required for doing this particular task. So to maintain the information about speculatively executed instructions and to ensure that the registers or memory locations are not modified until the validity of the prediction is confirmed. So the additional hardware is also needed to ensure that the correct instructions are fetched and dispatched in the event of misprediction also. So coming to this data dependencies. So the data dependencies we already discussed that. So if one instruction output is used as an input to the next instruction, then we describe it as a data dependency. So if we have a data dependency between the instructions, so it will impose the ordering constraint. So in what order the instruction has to be executed. So a simple approach is to dispatch dependent instructions in the sequence to the same execution unit where their order would be preserved. So independent instructions may be dispatched to different execution units. So for example, consider the add instruction dispatched to the arithmetic unit may need operand from load instruction. Okay, because the units operate independently and because other instructions may have already been dispatched to them, so there is no guarantee to when the results needed by the add instruction is generated by the load instruction. So a dependent instruction waits for its operands to be available. When an instruction is dispatched to an execution unit, it is buffered until all the necessary results from other instructions have been generated. So such buffers are called as reservation stations and they are used to hold information and the operands relevant to each dispatched instruction. So results from each execution unit are broadcast to all the reservation stations with each result tagged with a register identifier. So this will enable that the reservation stations to recognize a result on which a buffered instruction depends. So when there is a matching tag, the hardware will copies the result into the reservation station containing that instruction and the control unit begins the execution of a buffered instruction only when it has all its operands available. So in a superscalar processor using multiple issues, the disadvantage effect of stalls becomes even more noticeable than in a single issue pipeline processor. So the compiler can avoid many stalls through judicious selection and ordering of instructions. And coming to this out of order execution, so just we if you consider this four instructions in sequence. So here during the first cycle, these two instructions add and load are fetched, and during the second clock cycle, these subtract and store instructions are fetched, and subsequently in the coming clock cycles, these instructions will progress its execution. So the instructions are dispatched in the same order as they appear in the program. However, their execution may be completed out of order. So the subtract instruction writes to register R7 in the same cycle as the load instruction that was fetched earlier writes to R5. So if you see here the subtract instruction which is writing here to register R7 in the same cycle as the load instruction that was fetched earlier writes to register R5. Okay, so this is if the memory access for load instruction requires more than one clock cycle to complete, so execution of the subtract instruction would be completed before the load instruction. So if there is no dependency between a pair of instructions, the order in which the execution is completed does not matter because here for this load and subtract there is no dependency between these two instructions. So whatever the order if you are executing these two instructions does not matter. So the out of order execution exceptions. So the load instruction may attempt an illegal unaligned memory access for data operands. By the time this illegal operation is recognized, by the time the illegal operation is recognized, the subtract instruction that is fetched after the load instruction may have already modified its destination register. So program execution is now in an inconsistent state because the instruction that caused the exception in the original sequence is identified, but a succeeding instruction in that sequence has been executed to completion. So if such a situation is permitted, the processor is said to have imprecise exceptions. So the solution for this type of exceptions is that the result of the execution of the instruction must be written into the destination locations strictly in the program order we have to perform these operations. So delay writing into register R7 for the subtract instruction until after the register R5 for the load instruction has been updated. So either the arithmetic unit must retain the result of the subtraction instruction or the result must be buffered in a temporary register until the preceding instructions have written their results. So if an exception occurs during the execution of an instruction, any subsequent instructions and their buffer results are to be discarded. Now it is a reflection part for you. So what is this imprecise exception? Any students? Just now we described about what is imprecise exception. So execution completion to improve the performance, allow execution only when the operands are ready in its reservation station, may lead to out of order execution. So instructions must be completed in program order to allow precise exceptions. So there can be resolved if exception is allowed to proceed out of order, but the results are written into temporary registers. So this is what we are calling it as a commitment step. So the contents of these registers are later transferred to the permanent registers in correct order. So the effect of an instruction cannot be reserved after that point. So if an instruction causes an exception, the results of any subsequent instructions that have been executed would still be in temporary registers and can be safely discarded. So results that would normally be written to a temporary memory would also buffer temporarily and they can be safely discarded as well. So a temporary register assumes the role of the permanent register whose data is holding. So its contents are forwarded to any subsequent instructions that refer to the original permanent register during that period called the register renaming. We are calling that process as a register renaming. So when out of order execution is allowed, a special control unit is needed to guarantee in order commitment. So called it as the commitment unit is required. So it uses a separate queue, call it as a reorder buffer, to determine which instruction should be committed next. So instructions are entered into the queue strictly in a program order as they are dispatched for execution. So when an instruction reaches the head of this queue and the execution of that instruction has been completed, so the corresponding results are transferred from temporary registers to the permanent registers and the instruction is removed from the queue. So all resources that were assigned to the instruction, including temporary registers, are released. So the instruction is said to have been retired at this particular point. Now the reflection spot 2. So what is the role of commitment unit? So just now in the previous case we had a discussion on role of commitment unit. Now LVOs are revisited here. So after completion of this session, you will be able to understand what are the issues related to branches and data dependencies as well as out of order execution. Now the summary of this today's classroom discussion topic is branches can be handled by using branch prediction and data dependence can be handled by allowing execution of instructions in out of order. Execution can be completed by using commit point. So now the lecture level practice problem goes like this here. Assume that a program contains no branch instructions. It is executed on the superscalar processor. So what is the best execution time in cycles that can be expected if the mix of instructions consisting of 75% arithmetic instructions and 25% memory access instructions? How does this time compare to the best execution time on the simple processor using the same clock? So I hope you understood about this particular problem. So thank you one and all. Thank you students for joining for today's class.